in radars, we have in block 8, we have 3 units. Unit 18 is radars, unit 19 is types of radars, unit 20 is tracking of radars. In unit 18, we discussed basic radar system, which it can be divided, which it can be split into two methods, bistatic radar and monostatic radar. Next, we discussed about radar range equation. In this radar range equation, we are calculating power density from the transmitter side and receiver side, and from there we are calculating radar range equation, which we already discussed. Next, we saw the pulse radar schematic diagram of the pulse radar. In the schematic diagram of pulse radar, we have two sides. One side is transmitter, other side is in receiver. We are sending signals from transmitter to antenna, again from antenna to receiver, and we are checking here how the wave is simplified and how we are getting the signal across the receiver. Using receiver side, we are using the block called mixer. The one input of the mixer is local oscillator, other input of the mixer is radio frequency input. All these things comes under radars. Next, we saw in unit 19, we have types of radars. In types of radars, we discussed two topics. The one is the CW radar. Here, the full form of CW radar is continuous wave radar. And in this continuous wave radar, we calculate the value of frequency, and we saw the block diagram of CW radar, which can be treated this as one of the important essay question. Next, we saw MTIR radar. An MTIR radar is used for moving targets. This one is useful for the moving targets, which is using Doppler effect. This comes under unit 19. Today we will discuss the new topic called tracking of radar. Next, today we are discussing tracking radar. Tracking radar, in this we have three types. First, we will see sequential lobbing. We will see sequential lobbing, canonical scan. Next, we will see the amplitude comparison of the monopulse tracking amplitude. So we will see this one. Today we will start tracking of radar, which we can expect one of the short questions from this one. Out of these three, we will get one short question. Either the short question is sequential lobbing, canonical scan, or monopulse tracking amplitude comparison monopulse. Now after that, we will see these three comparisons. Here, first we will see the introduction part. In introduction part, it is used to determine the target. Why we will use this tracking radars? Tracking radars is used to determine the target's path. And we can find the position of the target material. Here, tracking radar system is used to determine the target path. And also we can estimate the future position. Future position means it is whether it is in the exact position, the tracker is in the exact position, or it is a slight movement either from left side or right side. We are checking using this tracking radars. Using this tracking radars, we can find out the range. Also, we can find angle, and we can find the Doppler shift using this tracking radar. So, tracking radar is used to determine the position as well as its range, and we can also calculate angle and also Doppler effect. So for this one, we are using one of the term called in the tracking radars is positioned in an angle. So these tracking radars, we are keeping one fixed position. Using which one? Using servo mechanism. This servo mechanism will produce an error signal. Actually, to this, suppose here I have tracking radar, which the signal is passing. Input side, I am using servo mechanism. Actual final destination is we want error signal is to be 0. We want 0 error signal. We want 0 error signal. So what is this tracking, actually meaning of this tracking and sequential? Suppose these are the images. Suppose my radar is here. We will see this one in the next coming topics. So finally, this is used to find the position, range, angle. To operate these tracking radars across the input side, what we are using? We are using servo mechanism system, and which final destination of is we want zero error signal. It is divided into three parts. First one is sequential lobbing, second one is canonical scan, third one is monopoles. First we will see the sequential lobbing. First we will see the diagram, afterwards it will be clear. This part is radar. This radar is connected to the antenna, and from this we are using two lobes. One is across position, one is used, another one is across position 2. So the target material is fluctuating in this between these two positions. So whether we have to cross check, and final conclusion is whether this target is near to position 2 or near to position 1. And when it is near to position or position 2, we have to concentrate that the error is 0. If error is 0, we are getting accurate. If error is not 0, then we have to try to adjust the position. That is called a sequential lobbing. Sequential lobbing. This is the diagram of sequential lobbing. So we have to concentrate that the angular error is 0. What is our intention? Angular error is 0. The difference between the position of the target and different direction is the angular error. What is the meaning of angular error? Suppose I want this one target across this point. Target has to be across this one. But what happening? There is a small movement of the target. Actual original, I want this one, but where we are getting this. So the small difference of this one is called as error. This we have to keep that error is 0. If error is 0, original angle and reference angle, both original one and reference are in both on the same axis. Original one and differences is to be in the same axis. Under these conditions, the target location is along the reference direction. So the sequential lobbing or lobbing switch is the simplest technique. It is used for the tracking purpose. In this, the direction of the antenna beam. So this antenna beam is continually switching between the two positions, which is shown in the figure 19.1. So here what we are doing, we have antenna. This antenna, I am switching between the two positions. The first position is position 1, second one is position 2. Between the two positions, position 1 and position 2. The strength of the signal from the target will fluctuate unless the target is positioned exactly midway between the two directions. What is the meaning of this one? Actually, it is fluctuating. Echo signal means some disturbance we are not getting. Some disturbance is produced. Actually, this is the position 1, this is the position 2, this is the target 1. It is fluctuating between this one. If it is not fixed exactly, we are getting disturbance. Is called as echo noise. So the distance between the two switched positions measures the angular displacement of the target from the reference axis. Finally, what we want, the error signal will activate the servo mechanism. Thus, the target can be tracked. Instead of this, easy explanation is from the diagram. Here in the diagram, what is observed in the diagram? We have two positions, position 1 and position 2. One antenna and other one is the radar. So the target material is trying to fix between the two positions, and we have to solve the error problem. And to this one, across the input side, we are using servo mechanism system. This is about sequential lobbing. Next, we will come to the canonical scan. Before discussing the canonical, sir, I want to show an example. What is here? This is the canonical scan. This blue color image is the canonical scan. This is radar, which is situated in the parabolic circle shape. And here I have target material. Whenever the radar is near to the target material, the amplitude of the signal is maximum. Suppose in the second case, see, where is the material? The target is here, but the radar is here. At that time, what is the amplitude of the signal? Amplitude of the signal is low. Amplitude of the signal is low. So this is canonical scan. Uh, Just a rough diagram I will show of the canonical scan. Suppose one paraboloid I'm using. I'm using one paraboloid and I'm keeping my target material here. I'm keeping my target material here. I'm now continuously rotating in all direction. What is this for? Canonical radar. Suppose target is here, canonical radar is there. But at the time, what is the amplitude of the signal? Amplitude of the signal is minimum. The amplitude of the signal is minimum. The amplitude of the signal is minimum. Suppose my radar is like it is rotating and my radar is in this direction. It is near my target element. If my radar is near the target element, at that time, the amplitude of the signal is maximum. This is called as the canonical lobing. In canonical lobing, just I will show the diagram. See here, here we have antenna. Here antenna is there. Here servo mechanism system. From this canonical shape antenna beam is searching for the target material. It is continuously rotating to check where is the target element. So it is producing two axes. One axis is called as beam axis. Another axis, whatever it is producing, it is called as rotation axis. The difference between these two, beam axis and rotation axis different, is called as what? Squint angle. I will show here once again in the image. What is squint angle? Squint angle is the difference between the beam axis and rotation axis. Now, let's see here. Here, one dotted lines is there. This dotted line represents beam axis. Another axis we have, this axis is called as a rotation axis. Like this, the beam is rotating in circular shape. Here, parabolic path is there. Like this, like this. It is canonical path is rotating. This rotation of the canonical path radar is called as beam is rotating in canonical way. And the difference between the beam axis and rotation axis, the difference between these two is called as squint angle. And actually your target axis is this one. The target axis is this one. Based on this, now we will see the explanation part of this one. In canonical side, what is continuously rotating? Offset antenna beam is rotating continually. It is searching for the target material. If the target material is near the antenna beam, then the amplitude is maximum. If it is far away to the target material, then the amplitude is less. This is achieved by mounting a parabolic antenna slightly off center and then rotating it about the axis of the parabola. However, this rotation is very slow compared to the pulse positioning frequency. What is pulse radar? Pulse positioning frequency means here it is pulse radar. It is used for both planes. It is useful for both. It tracks both the planes. Which planes? It tracks, one is azimuthal plane, another one is elevation plane. Whereas previously we discussed sequential lobbing is only for one plane. This is one for two planes. See here in the next paragraph, what is written? The angle between the beam axis and squint angle. The angle between the beam axis and axis of rotation is called as the squint angle. When the target is present within the squint angle, the echo signal will be amplitude modulated at a frequency equal to the antenna of the rotation. Means what is the meaning? Suppose if the squint angle is near to the target material, we will get the maximum amplitude of the wave. We will get the maximum amplitude of the wave, which it is shown here in separate images. See here, in this, the target is here. This white color is target. What is this one? That is radar. This canonical radar is far away to the target material. Just cursor, just observe. This is the target. This is the radar. These two are uh, in opposite directions. At that time, what is the amplitude of the wave? The amplitude of the wave is minimum. See the another one. The radar and target both are very close to each other. At the time, the amplitude of the signal is maximum. This is the main concept which we are seeing in the canonical scanning. So canonical modulation is extracted from the echo signal with the servo-mechanical system. So what is the function of the servo-mechanical system? The servo-mechanical system will continuously position the antenna. Means it is trying to position the antenna towards the target material. When the antenna is on the target, we are getting zero error. Means canonical scan modulation becomes zero. And the target is tracked by the canonical scan both in azimuthal and elevation. I will show here canonical scan. What are the main features of this one? We have one paraboloid antenna. Here I kept target. Here I have canonical shape radar. If these two are far away, the amplitude of the signal is minimum. Suppose another one, the theme of the topic. Suppose here paraboloid is there. Here I have target and my canonical radar, cone shape radar is near to the target. At that time, what of the signal? The amplitude of the signal is very much maximum. If there is a far, amplitude is there. So it will work in both the planes, azimuthal plane as well as elevation plane, whereas that one is only in one plane. One of the important here term, what is the another important term in this is, suppose if the radar, like this I have two axes, one is beam axis, another one is rotation axis. The difference between these two is called as squint angle. If the squint angle is almost near with the target element, then our error is zero. Error becomes zero. This is about canonical scan. Next, one more we have monopulse tracking system. Next one is monopulse tracking system. In monopulse tracking system is used, mono means one. Monopulse tracking system, here we are comparing amplitude. In amplitude comparison of monopulse technique, here in this monopulse tracking, I am here using 4 antennas. Those 4 antennas is horn antennas. We have different types of antennas. VHF antenna. Here this is antenna 1. This is antenna 2. This one is antenna 3. Next this one is antenna 4. 4 antennas is placed in a paraboloid reflector and arranged. See, 4 antennas are arranged which are displaced. 4 antennas which are arranged in a paraboloid reflector. From these 4 antennas, single pulse is producing, means from 4 antennas, single pulse is produced. Suppose here one single pulse. This is connected to A. This is connected to B. This is connected to C. This is connected to D. The output from 4 antennas, I am getting only one. Suppose if it is matching to the target material, the signal, monopulse signal is matching to the target material, but the receiver signal is the sum signal, sum of all the signals, A, B, C, D. Suppose it is small, actually this is target material. Suppose there is a small difference between the target material, then we'll call vertical difference signal. Another one is the horizontal difference signal. So when you will tell vertical, when you will tell horizontal signals, we will see here. Suppose 4 antennas. Antenna A, antenna B, antenna C, antennas. From these four, I am using only one output. That output is matching with our target. Then which type of signal is produced? Whatever the signal it is produced is called as sum of the signal. Suppose a little bit variation is there, it not exactly some error is produced. If the sum of the error is produced, the B and C is come. What is the B? What is the C here? B is the vertical difference signal, C is the horizontal difference signal. Now we will see the points related to this one, what is mentioned in this. So the four antennas are arranged which are displaced over the central focus of the paraloid reflector. Transmitter feeds the horn simultaneously. So we are taking some of the signal is transmitted. Mono means single. That single is the combination of four. Across the duplex, a duplexer is used across the receiver. And we will get the echo signals. Echo means disturbance of the signal. When you will get disturbance, if it is matching with the target, we will get the sum signal. If there is a small variation, we will get the vertical difference signal or horizontal difference signals. If the target is in the coaxial direction of the antenna, no difference will be recorded. At that time, we will get sum of the signal. If the target is in axial direction, means matching with the antenna. If the target is matching with the antenna, there is no difference. We will get the sum of the signal. Suppose the target position is deviating from the central position. If target is deviating from the central position, we will get vertical difference signal or horizontal difference signal. So the receiver will have three separate channels to receive the signals. Again, we will use filtered to separate these signals, but the signals are produced from again servo-mechanical system. The servo-mechanical system is here, acts as the input to produce the signals. So this is about monopulse tracking radar system. Next, we will see the comparison of the trackers. This you will get one of the short question. Now, which is the better one? Now, which is the better one out of three? Which three we discussed? We discussed sequential lobbying, canonical scan, monopulse tracking. Comparing these three, one canonical pulse tracking amplitude comparison is the first. Canonical is better, monopulse is better out of sequential lobbying. These points is mentioned in the 20.5 topic. Here what is written? Small paragraph easily is spent for 5 marks by writing two paragraphs. What is there in these two paragraphs? Which is better? See here, sequential lobbying one, canonical scan, another one is monopulse. Out of these three, canonical scan and amplitude comparison, monopulse is the better one. You have to write in the first paragraph. Next, in the second paragraph, why it is better? Why it is better means it is reducing noise, echo signals, disturbance problem is solved, whereas comparing with the first two, that is mentioned in the second paragraph. See, however, the signal to noise ratio is greater in monopulse compared to the accuracy of the tracking means we are getting exact outputs using which one? Monopulse radar system. This is about tracking of radars. So in this you study the three topics. The three topics what are the sequential lobbying, canonical scan, monopulse tracking, and comparison. If you study these four, 5 marks question is covered from the block on 20 or unit 8. Next, we will see the block 4. In block 4, we completed tunnel diode, Tapat diode, Barrett diode. But left unit 9 is left. In unit 9, what we have? Parametric devices. Now we will see about the parametric devices, which is page number 85 in your book. Now we will see the parametric devices. In parametric devices, we have only two topics, Manley-Roy power relation and parametric amplifier. This Manley-Roy power relation can be expected as a 10 marks question from block 4. From block 4, now we will see that one. Block 4. parametric devices we will see. In that first topic we have is Manley-Roy power relation. Now we will see what is this Manley-Roy power relation. Before that one, what is this parametric devices? We will see parametric device is used for non-linear reactance, or we can use this one for time varying reactance. Parametric devices are useful for non-linear reactance or time varying reactance devices. All varactor diode present whatever using that is also called as a parametric amplifier. Parametric amplifier. In this we will see first topic is Manley-Roy power relation. What is this Manley power? What you are observing from this diagram? I have one voltage source Vs. This Vs is called, I am calling this as a signal source. This is signal source Vs. Another signal source Vp. To this one, two resistors are connected. The first resistor here I am taking as a R. One more resistor is there. This resistor also treating as a R with two frequencies. First frequency is signal frequency Fs and second frequency is power frequency Fp. To this input side, I am connecting one capacitor. This capacitor is called as non-linear capacitor. And this is our capacitor. This is input side. This I will draw one vertical line, right? Here, which is input, which is output. This part is input. This part is output. Across input, what we have? Across input, two signal generators. One is Vs, another one is Vp. Next, two resistors. RR. These two resistors are represented with RR only. Next, two frequencies. One frequency is Fs, another frequency is Vp. This one is applied to the capacitor CT. Then we are getting two outputs. What the output we are getting? Fp plus F, sum and difference. Fp plus Fs is the sum of the frequencies. Fp minus Fs is the difference of frequencies. I am getting two frequencies with two resistors R and R. With two resistors R and R. So in the introduction part, what we have to write after drawing diagram, in the introduction part, what are the things we have to cover? In introduction, Manley-Roy power relation is a general energy relation. It is a energy relation regarding power flowing inside as well as power flowing outside from non-linear reactance. Take one non-linear reactance. In that, how much power is flowing inside, how much power flowing outside, we are concentrating. So here, what is the main point is, it is a energy equation. This is one of the energy equation. It is used for power flowing in and out of the non-linear reactors. Here, this C of T in the diagram. In the diagram, C of T, I am treating as a non-linear reactance. Description we will see. In the above figure, one of the signal generator is Vs. Another generator is pump generator. What is P here? Pump. P full form is here pump generator and their frequencies. What are the frequencies we have? One of the frequencies Fs, another frequency is Fp with two resistors Rs, and this one is connected to non-linear reactance. Here CT is treated as a non-linear reactance. Across the output, I am getting sum of the frequency as well as difference of the frequency. We'll see here. It accepts only one signal frequency and rejects all other frequencies. From frequency F and Fr, two applied frequencies, and I'm taking two equations, which is in page number 86. What are the two frequencies here I am concentrating? One is Vs, another is Vp. sum and difference of filters we are using, and here across the output we are using band pass filter. What is the function of this band pass filter? Band pass filter is designed to reject remind which frequency you want, only collect those frequency and reject remaining all frequencies. That is the function of the band pass filter. And here two frequencies, sum of the frequency as well as difference of frequencies, that is represented with m times of fp plus or minus n times of fs, where m and n are two non-integers. In this diagram, we have m and s. Sum of the frequencies plus difference of the frequencies minus. With two integers, I am concentrating. One of the integer is m and other integer is n. Now we will derive the equation. What is the first step of the equation? We have power signal, two voltages, power volt and signal voltage. What is power voltage? Vp cos omega pt. Signal voltage is Vs cos omega st. I have one equation, cos x equal to e power ix plus e power minus ix by 2. So writing cos in terms of e power ix plus e power minus ix by 2 and substituting here e power x. What is x here? X equal to j omega t. Again, this omega is writing one times of p, another times as s. So first I am writing only p terms, next I am writing s terms. So here Vp e power x plus e power minus x, two making separate, and first I am writing for the power equation the same way it is representing for the signal voltage. Like that I wrote 2. Next I am writing, what I am writing? Charge. I am concentrating capacitor is charging and discharging. First I am concentrating capacitor is charging. If the charging on the capacitor here is represented with Q. Q equals sigma m minus infinity to plus infinity. Q of m and e power j m times of omega p plus n times of omega st. This is the charge equation. This charge equation, how we represented? Same way, the same equation is represented in terms of voltage. The first equation is charge equation. Second equation is voltage equation. What is voltage? What is the difference between charge equation and voltage equation? Only one term is there. See, here I wrote Q of Mn. Here took V of Mn. Remaining all terms are similar. Next, I am differentiating dq by dt. dq by dt equals sigma m infinity to infinity. See here, e power j times of omega pt plus n omega st we have now. E power x differentiation. This e power x e power x, how we will write? Same way. Here, I am differentiating equation 3. Equation 3, what do we have? Equation 3 equal to, in terms of Q and E, that equation I am differentiating. So, exponent to x term, this is Q of Mn e power x. E power x differentiation is x times of e power x. Let's read this as a x, this as e power x, x e power x. Next, what I am doing from this? This J term and Q term. J term and Q term is treating as I of Mn. J term and Q term is treating as I of Mn. Now, same writing above equation, I equal dq by dt, sigma m minus infinity to plus infinity. In terms of J term and Q term, I am writing as I of Mn e power j omega Tn. This whole term is written where I equal to equation is written here. Next. Next, what I am doing here, I am writing power. The power consumed across the capacitor CT. Here CT is the pure reactance, and we are taking output. What we got output? F of P plus F of S or F of P minus F of S. For this, I am taking two integers m and n. So m times of F of P plus n times of F of S. Power equation I am writing V I star V star I, or I am writing in minuses. The first equation is in terms of plus, second equation is in terms of minus. What is the difference between here? The first equation I wrote power for Mn, only pure plus signs. Next equation I wrote power in terms of P of minus M, another one is minus N. Next what I did, total conservation of total power. Total power equation we have in the total power equation is sigma m equal minus infinity to plus infinity minus infinity to plus infinity, P of Mn equal to 0. P of Mn equal to 0. To this equation, I am multiplying numerator and denominator with m of omega plus n omega s, m omega plus n omega s. This one I am multiplying to the above equation. After multiplying, what is our original equation? The original equation is sigma minus infinity to plus infinity, minus infinity to plus infinity, P of Mn. To this P of Mn, I multiplied this term. M omega P plus N omega S, multiplied this one, numerator and denominator. Afterwards, what I am doing? I am separating denominator common, M omega P times of P of Mn, N omega S times of P of Mn. So this one I am splitting into two terms, which is equation number 7. Splitting into two terms. What is the first term? First term is M omega P. The first term is M omega P. We'll open this again. We are discussing this one. After multiplying numerator and denominator, the two terms. First one is m omega p times of P of Mn. That is first term. Next term is n omega s times of P of Mn. So this is first term. This is second term. Now I am equating 0, these two terms individually. First term is making to 0. Second term is making to 0. What we will get? We will get equation number 8 and equation 9. After that, in terms of omega, I am writing in terms of frequency. Same, 8 and 9 is same. What is the difference between 8 and 9? In 8, the equation is written in terms of omega p and omega s. Equation 10 is right in the form of fp plus fs. Again, equation 9 and equation 11 is also same. What is the difference between 9 and 11? What is the difference between 9 and 11? In 9, the equation is in terms of omega p and omega s. Whereas here in terms of fp and fs. So the above two equations is called as Manley-Roy power relations. You will get this as a essay question. Derive the equation for Manley-Roy power relation. With the two frequencies, I am writing for FP and FS. What is FE? Pump frequency for the pumping oscillator. And FS is the signal frequency for the signal generator or signal oscillator we will call. Again, what I am doing in this is, what is our final equation? In this, I will substitute m equal to 1001. I will show that one how to write. Suppose in this equation 10, I am substituting m equal to 1, n equal to 0. What we will get equation? If m equal to 1, numerator is P of Mn, P of 10. If I substitute like this, what we will get numerator? P of 1, 0. Denominator is f of p. Denominator is 1 times of f of p as n is 0. Those are writing down. Let's see the next one. What is this equation? M equal to 1, n equal to 0. One condition. What we will get? This one. Second condition is m equal to 1, n equal to 1. If both are 1, we will get this one. P of 1, 1 by f of p plus f of s. So this is equation 12. Next, another condition. So the main conditions here is one is m equal to 1, n equal to 1. Along m equal to 1, n equal to 0. Next condition is reverse. N equal to 1, m equal to 0. With m comma n equal to 1. If you substitute this one, we will get equation number 12 and equation number 13. So P of 0, 1 in the equation number 13 and equation number 12, P of 1, 0 and P of 0, 1 are two power generators by the two voltages at frequencies f of p and f of s. P11 is what? When two integers m and n both are equal to 1. Then we will get P of 1.1. So this is a Manley-Roy power relation. Afterwards, we have power gain formula. After writing this, you have to write about the power gain formula. The power gain formulas, two power gains we have. The two power gains is for the up converter and down converter. If the power gain for the up converter is f of p plus, it is the ratio of sum of the frequencies by signal frequency. What is the sum of the frequencies? Here the two sum of the frequencies I am taking as fp plus fs and signal frequency fs. Here fp plus ff is treated as f0. So parametric up counter is a ratio of f0 by fs. Next, one more we have parametric down counter. In parametric down counter is reverse. fs by fp plus fs. fs by fp plus fs, reverse. So in the numerator, if we have fp plus fs, that is parametric up counter. In the denominator, if we have fp plus fs, that is down counter, where f0 equal to fs minus fp. So this is the final of Manley-Roy power relation. This one learn from fourth to get essay question from the fourth unit. This Manley-Roy power relation. Just we will recall once again what we discussed in this Manley-Roy power relation or parametric up and down counter. Just a recall. First, what we have to give in the introduction? We have two signals, Vs and pump signal Vs, pump voltage Vp with the two frequencies Fs and Fp with the two resistor R. These all is input side. This all from the cursor point. All these are input side. This one like this you have to give. This is input part. Applying to non-reactance capacitor, you will get output part. The main function is here CT. Using this, what we did? After writing this, two signal voltages taken. One signal voltage is Vs, another signal voltage is Vp. And sum of the two signals done. In place of cos, I substituted e power x equal to e power x plus e power minus x by 2. And I wrote here charge formula. After writing charge formula, again the voltage formula is written. Again current is calculated. Current is calculated for dq by dt. Q equation, whatever we have, I did differentiation. After differentiation, power conservation power final equation is written. The conservation power equation is written. After writing conservation of power equation, multiply numerator and denominator with m of omega p plus n of omega s by m of omega p plus n of omega s. Or take individual terms and equate to 0. After equating it to 0, you will get 4 equations. 2 equations is in terms of omega, 2 equations is in terms of frequency. After writing this, your Manley-Roy power relation topic is over. After that, substitute power gain formulas. We have two power, these. For the, after getting equation, treat once, two cases, m equal to 1, n equal to 0, n equal to 1, m equal to 0. After substituting, we will get 12 and 13 equation. Afterwards, calculate power gain for the up counter and down counter. This is about what? This is about Manley-Roy power relation. Next, we have another one, parametric amplifier. Just in oral, I will explain that one in this. There we have page or not exact. Empty space. I'll write on the whiteboard. Next topic is parametric amplifier. We can expect this parametric amplifier as a 5 marks question from the previous year question paper. This is a 5 marks question. In this parametric amplifier, we have two sides. Just I will show the diagram. Here I have capacitor. To this capacitor, one side I connected resistor combination. There is a this I have one capacitor. So this capacitor, all these things rounded escaped. Here one capacitor is there, which is page number 89. Ma. To this capacitor, the name of the capacitor is CT. We'll draw here. One resistor. Pen. One resistor RS, two resistor, one inductor, to this inductor, one capacitor, one resistor, here, one resistor. A bit closer, I will say again. Share. or else I will show direct image. Screen is not there. I will show the direct Google image of this one. Share screen. Yes. I will explain the diagram from the direct parametric amplifier. In parametric amplifier, directly I will explain the diagram here. This is the image. Just observe the image. What you are observing in this image? Here, capacitor, two sides is there here, pump circuit and signal circuit. Here, main CT is our thing, important thing is here CT. To this one, I'm applying two types of signals. What two types? One is signal circuit. What are the things is there in the signal circuit? One resistor, one inductor, another capacitor. Resistor is RS, inductor is RL, inductor is LS, and capacitor is CS. And another I'm applying pump circuit. This cross diagram is represents the pump circuit. The box diagram represents signal circuit. This from here to here. See the movement of the cursor. This is signal circuit. The cross diagonal diagram. What is the diagonal diagram here? RP, LP, CP with current IP. This is called as pump circuit. These two circuits are connected with CT and load resistor RD. After applying this, we are getting output. What is our output combination? Output is CL, L, LL, RL. So we have input side and outputs. Based on this, just try to write here. What are the inputs we have for signal circuit? For signal circuits, inputs are RS, LS, and CS. These three belongs to signal circuit. Next, I'm checking for the pump circuit. What are the things we have for pump circuit? RP, LP, CP. These two I applied to the capacitor CT. These two I applied to the capacitor CT. After applying to the capacitor CT, what I will get, the output I will get is ideal circuit. CL, another I am getting inductor LL, another I am getting resistor RL. So you have to describe the circuit. What are the signal circuit we have inputs? To the signal circuit we have inputs is RS, LS, CS is signal circuit. Next pump circuit is RP, LP, CP. These two are applied to the capacitor. The output is CL, RL and CL, RL and LL. From this, I am concentrating on the frequencies. Whatever the output I will get, that I am writing as a F0. The output F0 is equal to M and N are two integers. M times of F of P, pump frequency, plus or minus N times of signal frequency. N times of Fp plus or minus N times of Fp. Here, suppose F0, whatever F0 we have, if it is greater than Fs, if F0 is greater than Fs, I'm calling this as a parametric up. Parametric up. Suppose F0 is lesser than another condition we have F0. This F0 is lesser than Fs, then it is called as parametric down counter. So in the final is what we have to do, draw the diagram. Afterward, total frequencies M times of F of P plus or minus N times of F of S. If output frequency F0 is greater than Fs, we will call this as a parametric up counter. If out frequency F0 is lesser than Fes, we will count as a parametric down counter. After this, we have to write equations. Next subheading is parametric up counter. In up counter, what are the things we have to cover? We have to write the gain formula. Here the gain formula is equal to, we have gain formula. Gain formula equal to F0 by Fs by under root of x by 1 plus under root of 1 plus x 1 plus x whole square. This is the formula for the gain, where what is F0? Where F0 equal to source as well as pump frequency. Source frequency as well as pump frequency. From this, next you can write noise margin formulas is there, which you can refer in the textbook. Next it comes to the parametric down converter. In parametric down converter, what are the steps we have in parametric down converter? We have parametric down converter. In parametric down converter, what are the things we have to concentrate? In parametric down counter, we have Fs equal to Fp plus F0. From this, write the formula of power gain. Power gain formula equal to Fs by F0 times of x by 1 plus under root of 1 plus x whole square. So, this is the formula of parametric down counter. So, in the model questions, page number 90, you have two questions. What is the first question? Derive Manley-Roy power relation, which it can be expected as a 10 marks question. Next, another question is there, explain parametric up and down counter, which it can be treated as a 5 marks question. So, block 4 is completed. Parametric device is completed. And radars, still now we completed block 2, block 3, block 4, block 5, block 6, block 8. Block 1 and block 2 is left. Now we will see next topic is block 1. In that what we have, 3 units we have in block 1. That is unit 1 is passive devices. Unit 2 is cutoff wavelength. Unit 3 is rectangular waveguides. This unit 1 and unit 2 can be expected as a 5 marks question, and unit 3 question can be expected as very important 10 marks question. Now we will come to block 1. Unit block 9 completed. This is completed. Even completed. Next we have unit 1, 2, 3. In unit 1, 2, 3, what are the things, which questions can be expected as essay, which questions will be expected as short? We will see all these. First, so unit 1, block 1. In this unit 1, passive devices, waveguides, as well as cutoff wavelength, we will see. First, what is the main theme of studying this chapter? In this, we are studying about the waveguides. Where we are using these waveguides? Waveguides are used at microwave frequencies for transmission as well as for receiving side. For this, we will discuss few terms. What are the terms we will discuss? Phase velocity, group velocity, which type of waveguides we are using, at what frequencies these will be applicable and these will be useful. We will see all these things. So in the introduction, what is covered? First, we will see the objective of this one. The concept of waveguides are used at microwave frequencies. For which purpose we are using? We are using this one for transmission of signals. For transmission of the signals. in the introduction part, which type of signals we are transmitting from transmitter to, suppose, imagine here I have transmitter. With other side I have receiver. From transmitter to receiver, whatever the signals I am sending, those signals is called as electromagnetic energy. This electromagnetic energy, EM, this electromagnetic energy is transmitted from transmitter to receiver. That is mentioned here. In communication system, radio frequency energy is transmitted from where to where? Transmitter to receiver. So whatever the device we are using for transmission, that is called the device used to transfer this radio frequency energy with minimum loss is called as a transmission line. Here which comes under transmission line in this? Suppose here transmitter is there, this side receiver is there. To transmit radio frequency signal, the path through which we are transmitting, this is called as a transmission line. This one is called as a transmission line. That is mentioned here. So, for transmission purpose, we will use parallel wires, arrays, coaxial cables, etc. we are using. Suppose we have, again, the topic will be diverted. Parallel and sequence. In general, what is the meaning of parallel transfer and sequential transfer? In general, what is parallel transfer and sequential transfer? Suppose here I have transmitter, and that's the other side I have receiver. 8 bit of data is transmitting using 8 lines. How many lines covered? 1, 2, 3, 4, 5, 4, 5, 6, 7. One more we take. So this is transmission of data through parallel. This is called parallel mode of transmission. Another transmission mode we have serial mode of transmission. In serial mode of transmission, transmitter is there, receiver is there. In this, only through single channel we are transmitting. So in general, in this transmitter and receiver, which method we will use? Suppose sender is one side, receiver is other side. From sender to first, I am going serial communication. Next, parallel communication. Again, serial communication. Again, across receiver. This is receiver. So, serial to parallel will not go directly once at a time. In the middle, what we have? In the middle, I am using both serial as well as parallel. First, which field I am using? To transmit from sender to receiver, first use serial concept. Suppose from Hyderabad to Bombay, means smaller distance, serial is okay. From Hyderabad to America, is serial communication suitable? No. So, starting side, ending side, we are using serial. Starting side, ending side, we are using serial. In the middle, we are using parallel communication. So, this channel, whatever we are using, this line is called as a transmission line. Sending a signal through the line is called as transmission line. We will come to our original topic. So, what are the transmission lines? Which type of transmission lines we have? Either parallel wires or coaxial, etc. we are using. And this radio frequency, if the frequency of the radio frequency is greater than 3 kilohertz, 3 gigahertz, then we will use hollow metallic tubes. If it is lesser than 3 gigahertz, 3 gigahertz lesser than, then we will use parallel lines or coaxial lines. We will use either parallel lines or coaxial lines, less than 3 gigahertz. Suppose the radio frequency signal is greater than 3 gigahertz, then we will use metal pipe or tube with any cross section is used. In some cases, we are using coaxial tubes. Also, whatever the for wave transfer, what are the wave it transferring, that is as here two terms I am using. The wave is called as a guided wave, in which we are transmitting is called as waveguide. Suppose we are transferring signals using coaxial cable అనుకోండి, నేను signals ని coaxial cable తో pass చేయాలి. So that coaxial cable is comes under here as a waveguide. Whatever the wave we are sending, that wave is called as guided wave. See what is this figure A and figure B? Figure A shows the rectangle shape waveguide is called as rectangular waveguide. This is in rectangle shape. Another waveguide we have, this is circular wave. So here we are seeing two definition. Wave ni పంపించేదాన్ని waveguide అంటాం. That wave ni through what we are sending, that is called as a waveguide. Here we have two types of waveguides, rectangular waveguide and which is shown in figure A. Another one is circular waveguide which is shown in figure B. One more here we have to concentrate is the area of cross section of the waveguide. Here the area of the cross section of the waveguide is same as the wavelength of the signal. If the cross-sectional area of the waveguide is same as the wavelength of the signal, at the time up to 1 gigahertz of frequency, no need of using. Suppose another one we have, if waveguide dimension is decreasing. If waveguide dimension is decreasing, what happens to frequency? Frequency is increases. Suppose frequency is decreasing, we have to use waveguide dimensions to be in increasing manner. So both are in opposite. Which two are in opposite? Waveguide dimension and frequency. Both are in opposite. And no need to use for less than 1 gigahertz of frequency. 1 gigahertz of frequency. This is mentioned in this page. And in the next page. So which topic is this one? These are completely about introduction of the waveguides. In the second paragraph, he is explaining about the voltage and current. If voltage is maximum, what happens to current? Current is minimum. That is non-ohmic law. Ohm's law ante V equal to IR kada, Ohm's law. V equal to IR. R equal to V by I. As we studied previously, here in this second paragraph is explaining about ohmic and non-ohmic. With this ohmic, non-ohmic is in terms of whether voltage is increasing or voltage is decreasing mode. We will see that one here. In the waveguide, voltage and current are distributed very complicated manner. If voltage is maximum, what happens to the current? Current is minimum. If voltage is minimum, current is maximum. So, instead of discussing in terms of voltage and current, it is convenient to discuss in terms of electric and magnetic fields. So instead of discussing voltage and current, in which terminology we are using? We are using electric and magnetic fields within the waveguide. So electric field is perpendicular to the magnetic field. As we know this one, electric field is perpendicular to the magnetic field. This is explained in the second paragraph. Next, in the third paragraph, to discuss these electric and magnetic fields in the waveguides, compulsory we have to concentrate on the Maxwell equations with its boundary conditions. We have to concentrate Maxwell equation with the boundary conditions. This one we have to configure in the different modes. What is different modes? TE, transfer electric field with 1-1, transfer electric field with 1-0 mode, transfer electric field with 0-1 mode. All these are called as different modes. That is explained in the third paragraph. Next, come to the fourth paragraph. Only given in the fourth paragraph is the advantages of the waveguide. What are the advantages of we have in the waveguide? Only they will ask short question, explain about the advantages of the waveguide. If they ask about the advantages of the waveguide, what is the first point we have to cover? It is used for For power handling issues, we are using these waveguides. That is the first point is given here. It has power handling capability. This power handling capability is 10 times greater than coaxial lines. So, what is the meaning of dielectric medium? Dielectric medium means air. Here, dielectric medium is air. So, when the wave is propagating, suppose wave is propagating. What happens? Suppose like this, the wave is going inside. What happens? If it is goes straight, it will not continue until the end. We have to use whatever the way we are going. Actually, it has to be the zigzag waves. Which type of waves we have to use? We have to wave the zigzag waves. So, in the introduction, in 4 paragraphs, what is discussed? In the first paragraph is discussed about we have the data is transmitted using parallel lines as well as using parallel cables as well as coaxial cables. Suppose if the radio frequency is greater than 3 kilohertz, then only we will use this type of one. Next, another one, what is said here? What is the definition of guided wave? What is discussed in the first paragraph? What is guided wave? And that is what is waveguide. Just get the differentiation of these two, what is guided wave and what is waveguide. Next, in the second paragraph is discussed about the relation between the frequency and the dimensions of the waveguide. If frequent in the second paragraph, what is discussed in the second paragraph? If frequency is maximum, waveguide dimensions is minimum. If frequency is maximum, waveguide dimensions is minimum. This is discussed in the second paragraph. Next, in third paragraph, what is discussed? In third paragraph, because it is difficult to discuss the voltage and current relations. So instead of discussing voltage and current relation, we will talk in terms of electric and magnetic fields. This is in the paragraph 3. Third paragraph is explained about the relation between voltage and current. It is difficult to discuss in terms of voltage and current. So we will discuss in terms of electric field as well as magnetic field. Always remember, electric field and magnetic field both are perpendicular to each other. That is covered in the third paragraph. Next, what is covered in the fourth paragraph? In fourth paragraph, he said, to solve this electric field and magnetic field equations, compulsory we have to concentrate on which equations? Concentrate on Maxwell equations. To simplify this electric field and magnetic field, we have to concentrate on Maxwell's equation with boundary conditions, with different modes. What are the different modes means here? Suppose I am using transfer electric field Mn. In this Mn, I am using transfer electric field for 10 mode, transfer electric field for 01 mode, next transfer electric field for 11 mode. Like we have to operate in different modes. Next, these were explained. Next, in the last paragraph, what is explained? What are the advantage of using waveguides? Using the advantage, we have to cover the point that it is useful for power handling. For which one it is useful? It is used for power handling. It is used for power handling. Um, so which is better? Suppose the wave is propagating, it is colliding with the walls. So that which type of lines we have to use. All these things are explained in introduction. Next, we will come to the topic 1.2, reflection of waves from conducting plane. We will see. Hmm. Next one is reflection of wave in the conducting plane. What is this reflection of wave in the conducting plane? Means suppose the wave is traveling from source to destination side. At that time, how the wave has to be? Suppose if the wave is transmitting from source to destination in straight line, it will not reach up to the end. It is colliding with the walls. Walls నుంచి collide అయిపోయి అక్కడనే die అయిపోతాయి. So how we have to transfer the wave? The wave has to be transferred in zigzag manner. So this one is explained in this. In order to understand the electromagnetic wave, how it is propagating in the waveguide, we have to we have to see the conducting plane. In general, we know that electric field and magnetic field both are mutually perpendicular with each other. Suppose when the wave is traveling straight, what happens? It is short-circuited by the conducting walls. Short-circuited by the conducting walls means ఏంటి? Suppose ఇట్లా wave transfer అవుతుంది. ఇది walls కి collide అయ్యి అక్కడనే die అయిపోతుంది అన్నమాట. Conducting walls తోటి collide అవుతుంది. So don't use straight waves. Use which type of waves? Use the waves which are in zigzag fashion. At that time, it will not collide with the conducting walls. So if we are using zigzag, at that time what happens? Electric field is maximum near the center of the waveguide. Across the conducting walls, the electric field is 0. Here two important points. Electric field in the center is maximum. Electric field across the center is maximum. Next, electric field across the conducting walls is 0. Suppose wave is incidenting. All these bases are in intermediate. Suppose incident wave. When the wave is incident, obviously it will be reflected. And also we are concentrating on normal to the plane. So incident wave, reflected wave, and normal to the plane. To this one, incident wave is represented with VI. Normal to the plane is represented as VR. This is VN. This one again operating in different modes of operation. Now we will see what is TE mode, what is TM mode. In TE means transfer electric field. In transfer electric field, there is no component of transfer electric field. Electric field undadu. Propagation direction, there is no electric field. Not that no complete electric field. Electric field is there, but there is no electric field in the direction of propagation. Signal. What is TE? What is TM? TE full form is transfer electric field. TM is transferring of magnetic field. In transfer of electric field, there is no component of electric field in the direction of the propagation, which is known as transfer electric mode. Another one is there. Transfer magnetic field means there is no magnetic field in the direction of the propagation. Direction of propagation lo electric field lekapothe TE mode. Direction of propagation lo magnetic field lekapothe that is TM mode. See this one. Suppose a wave is insulating like this. Wave is insulating. When the wave is insulating, I am concentrating the angle of velocity. Two velocities I am concentrating to this incident wave. One is group velocity Vg, another one is group velocity Vg, another one is phase velocity. And one more velocity we have conducting surface velocities. Conducting surface. And normal to the plane I am calling as Vn. Normal to the plane is Vn. In this diagram, to the incident line, whether across the direction of propagation, we are using the three terms. One is Vg, group velocity. Another one is Vn, normal to the plane. Velocity is normal to the plane. Another one is Vp. Vp is conducting to the phase velocity. V is phase velocity. Based on that, I am writing two equations. What are the two equations? First, group velocity equation. Group velocity Vg equal to what is group velocity? Group velocity Vg equal to Vc sin theta. What is Vc here? Vc is actual velocity of wave. Vc is actual velocity of the wave. Writing in terms of time theta is Vg. Next, I am writing velocity normal to the plane. Velocity normal to the plane I am writing as Vn. Vn equal to Vi cos theta. Based on this, I am calculating two wavelengths. All this is happening in the direction of propagation. We are deriving complete equations in the direction of propagation. Here I am taking Vg and Vn, two velocities. What are the velocity? Group velocity, velocity during the normal plane. To this one I am writing wavelength lambda g and lambda n. Writing two formulas. Lambda p. What is lambda p formula? Lambda p equal to lambda naught by sin theta. Another formula lambda n equal to lambda naught by cos theta. From this, we can measure the wavelength across the direction of propagation. We can measure the wavelengths across the direction of propagation. Next, we will see the phase velocity. Phase velocity is Vp. Actual phase velocity formula is Vp. Now, Vp equal to F times of lambda p. But what is lambda p? From the above, lambda p equal lambda naught by sin theta or Vc by sin theta. V equal to n lambda. We know general equation. V equal to n lambda. Velocity of light is 3 into 10 to the power of 10 is given. Vg equal to... So finally, here we are calculating phase velocity. We are calculating phase velocity. Phase velocity equal to F times of lambda. In the above equation, we have lambda equal to lambda naught by sin theta. And writing that one, we will get 1.5. In this, we have another one, parallel plane waveguide. Suppose I will explain the parallel plane waveguide. First, we will see diagram and then you... the diagram. First, I will explain the theme of this one. Next, we will see the image. First, suppose the wave is transmitting. Suppose the wave is transmitting. One is open side, another one is closed side. Is it? One is open side, another one is closed side. Whatever the wave it is transmitting, suppose other side is short circuited. What is the meaning here? This one is short circuit. And here what happening? Voltage is zero, current is maximum. Like this we have. One is voltage and another one is current. From this, what conclusion can be given? Voltage is maximum. Voltage emo zero untundi. Current em untundi? Maximum untundi. Next, we have one more diagram. Suppose this is my open end. Suppose I am taking closed end here. First set. In second set, I am shifting my closed end a little bit front side. This is second part. Every time closed circuit ne munduku jarpali. Next, here closed end I moved a little bit. Move forward. Next, open circuit ఉంది. Closed end is very near. So each time closed circuit ని shift చేస్తున్నాను. At that time, what happens is explained in the figure. Suppose here you have, suppose this one is my end part. At that time, total wavelength is 3 lambda by 2. Total wavelength is lambda by 2. Suppose I shifted here. What happens? I shifted here. What happens? That is given in the diagram. This is the image. What is the first image? What is the second image? What is the third image? Topic is parallel plane waveguide. One side is always open. Second side is closed circuit. See the first diagram. What is the first diagram here in this? Here you have one dotted line, one dark line. This line is current line. Straight bold lines is current line. Current is always maximum. Voltage is minimum. V equal to 0. This is the conclusion from the diagram. And from above diagram, input side is open. Output side is short circuited. Close in the output. And next diagram. This short circuit every time I'm shifting. Suppose short circuit is here. From the beginning point, what is 3/2? This is first short, second short. Next short circuit is shifted here. Next short circuit is shifted here. Every time the wavelength is changing λ/2, 2 λ/2, 3 λ/2. Next figure is about, see here, direction of propagation with the different wavelengths. This is the third diagram. So this is the reflection of wavelet. In the reflection of waveguide, only one important point is one side is input open, output is close. This output close, every side I am moving a little bit front side. Then how the wavelength is varies. So from this we can expect 3 questions. These 3 questions can be 5 marks questions can be extended. What is the first question? What is phase velocity? What are the advantages of waveguides? Next is discuss the reflection in parallel waveguide. These are the 3 short questions can be expected from unit 1 in block 1. In the next class, we will see what is cutoff wavelength and we will see rectangular waveguides, which is 10 marks question in the next class.